Hello, Five Keys. Mr. Mike here. I thought you might enjoy the ride up on the desk. Here we go. Isn't this cool? We are working on module 5, lesson 2 today, direct variation. Okay. What's hard about direct variation is not the mathematics. What's hard about direct variation is the language. There's a lot of it. So just bear with it and remind yourself, hey, the only thing really tricky about this is all the crazy words. All right. So I will give a quick introduction and then we will hop on into whatchamacallit, the worksheet. Okay. So direct variation, I'm just going to erase all of this. I started the video, then had to stop it. That's why there's stuff here. Okay, so direct variation. You will know when you're looking at a equation that has a direct variation relationship because it will be in a form of y or some variable is equal to k, some constant, times x. What does that mean? Well, it means that there is a dependent variable y that is equal to some number like 3 times a independent variable x. So for instance, in the case of y is equal to 3x, I can plot this very clearly. When x is 0, y is 0. When x is 1, y is 3. When x is 2, y is 6. When x is 3, y is 9. There's a constant number that's multiplying the independent variable to get the dependent variable. In this case, it's 3. That's all it is. These graphs that have direct variation, if we want to look at a visual of it, the y and the x, because they are variables, are pictures, right? They are, it's more of an image than it is that we're solving for a number. We're solving for a series of numbers that can make an image. They can make a line. In this case, y is equal to 3x. Let me do it in a different color. And I'm making a point of this, even if it seems kind of obvious, because math is turning on us at this point. We've been accustomed to getting a problem that was like, hey, solve for an unknown, solve for x, solve for y, and here's the expression, or solve y in terms of x, right? And we're just moving things around. What that was building to is we're arriving at it now. Now we're actually solving for a picture. So if I say y is equal to 3x, I may say something like graph it. And what I want to know is what that line looks like. Or I can give you the line and say, give me the sentence, right? Y is equal to 3x, or the equation. It's not dissimilar to say me using the words pink elephant, and your mind creates an image of a pink elephant. Or I show you a picture of a black hat, right? And you write out in words a black hat. The equation, the y equals 3x, I wonder if I deleted that. I hope I didn't. The equation y equals 3x is the word black hat. This line is the image or the thing, the black hat, all right? So what we are is we're creating a language with numbers and letters that draws pictures, that gives us images. It's a language. It functions the same way. Okay, I can go crazy down that rabbit hole, but I won't. So let's pull up the assignment to keep Mr. Mike on track here. All right. Okay, Unit 5, direct variation, the learning target, students will be able to write and graph an equation of direct variation. Write and graph an equation. I just kind of talked about what that means, right? The graphing part is the image of the pink elephant. The right part are the words pink elephant. definition, direct variation, mathematical relationship between two variables that can be expressed by an equation in which one variable is equal to a constant times the other. Oh my gosh, that sounds super complicated. It is not. A mathematical relationship is simply an equation or something like it. It's between two variables. A variable is a little bit different than an unknown in that it's going to vary. It is the axes, right? If there's one that's going to be independent, there's one that's going to be dependent, and we can graph them in relationship to each other. So a relationship between two variables that can be expressed by an equation, that means there's an equal sign, in which one variable, let's call it y, is equal to a constant, let's call it k, and k is just filling in for any real number, times the other variable, let's call it x. Y is equal to kx. All right, scrolling down. So there is a direct variation relationship between how far thunder is or lightning is and when we hear it. So when we see it, lightning, and when we hear the thunder. And we're going to call that the rate of change, meaning the change in the dependent variable is on top and the change in the independent variable is on the bottom. If this is sounding really familiar, it's because it is. This is slope. We've discussed slope and length in module 4. There is no difference between rate and change in slope. In fact, that direct variation constant is slope. Rate of change, direct variation, slope, same thing. Okay. So if this were a graph, the y, that's my dependent variable. The x, that's my independent variable. Change in y, I'm using the delta symbol. We've seen it in module 4. We're going to be reintroduced to it in module 5. Change in x, change in dependent, change in independent. If we're starting at 0, they're giving us 2 numerical expressions to come up with the answer. The change in the dependent is 5. The change in the independent is 2. 10 divided by 2 gives us the rate of change. It's 5. They took another data point. They came up with 15 seconds and 3 miles, 15 over 3. That rate of change is constant, meaning there's direct variation. If we were to go to 4 seconds, we would get 20. If we would go to 5 seconds, we would get 25 seconds. I'm sorry, 5 miles, we would get 25 seconds. Okay. Let's look at 2 equations. What if I don't want to? So now we're not going to look at this visually so much. We're going to do some algebra. Let's see if either is a direct variation. What does that mean? For it to be a direct variation, it needs to be in the form y is equal to kx, where k is a constant, so k is a number. So they give us an equation, 7y is equal to 2x. The instructions that they're giving us is to solve for y, why, so that it can look like this, okay? So they divide both sides by 7 so that we have 1y, which is what we want. And they come up with y is equal to 2 over 7x. Yes, this is a direct variation because k is 2 over 7. K does not need to be an integer, it does not need to be a whole number. It can be any real number. In this case, it's 2 over 7. They give us another equation, 3y plus 4x equals 8. Solve for y. They do. They take the 4x and they bring it to the right side of the equation. They divide each side of the equation by 3, and they come up with y is equal to negative 4/3 x plus 8 over 3. This is a linear equation, meaning it does make a line, but it's not a direct variation because of this 8/3. All right. Yeah, and we'll see more what that looks like visually in a later lesson. Wow. The equation y equals kx will be used with substitution of two of the variables to find the third. Ignore that. That's a really confusing and frankly incorrect way of phrasing it. K is not a variable. That's why that's wrong. That's wrong. K is not a variable. K is a constant. So I would rephrase this. The equation of y equals kx will be used with substitution of the variables to find the constant. You can say that. So suppose y varies directly with x. So we know the equation is going to be in the form y is equal to kx, some constant times the variable, because that's what it means for y to vary directly with x, literally. And y equals 35 when x equals 5. When, because these things are variable. X and y are going to change, right? So what direct variation equation relates x and y? Okay, well, I have 1 point. I know that when x is 5, y is 35. So what do I need to multiply 5 by to get 35? In other words, when y is 35, there is some number k that I can multiply 5 by to get 35. Well, if I divide both sides by 5, I end up with 7 equals k. Y is equal to 7x. Here we go. That is my equation. Okay. So what direct variation equation relates x and y? This one right here. What is the value of y when x is 9? Well, now I have an equation. I don't need to worry about k. I only have 2 unknowns, and they're giving me one of them, the variable. So I'm just going to plug in. That's so confusing. I'm going to plug in 9 for that 7. So I'm going to end up with y is equal to 7 times 9. And I'm going to end up with y is equal to 63 for x is equal to 9. Okay. Okay. Let's clear that. Boom. Let's scroll down and see what else they got for us. Suppose y varies directly with x and y is equal to 10 when x is equal to -2. What direct variation equation relates x and y? What is the value of y when x is -15? Same exact problem. Let's take a look at how this works. So y varies directly with x. So I know that y is going to be equal to some constant, I'm going to name it k, times x. I also know that when y is 10, x is -2. So when y is 10, there is some constant k by which I can multiply -2 to get to 10. So I'm going to divide both sides by -2, divide both sides by -2. I know that this goes to 1, and I know that 10 divided by -2 is -5. Now I can plug my k back into the general form of the direct variation equation and end up with y is equal to -5 x. That is the first part of my answer. Boom. What is the value of y when x is 15? Well, now that I have a general form of an equation, I can use substitution. to evaluate and I end up with -5 times -15, which gives me y is equal to 25 positive, because a negative times a negative is in fact a positive. Da-da-da. So there's our two answers. Y is equal to -5x. That is the direct variation equation that relates x and y. And when x is -15, y is positive 25. Scrolling down, let's see what else we got. We got an example here. Space exploration, weight on Mars, y, varies directly with the weight on Earth, x. The weight of the science instruments on board the Phoenix Mars lander on Earth are shown below. The weight on Mars is 50 pounds and the weight on Earth is 130 pounds. What is an equation that relates weight in pounds on Earth and weight on Mars? Well, we know that they vary directly. So y is going to be equal to, what's going on? That's not right. Y is going to be equal to kx. Y is our weight on Earth, so they're substituting in 50. Weight on Mars is our, weight on Mars is our y, so they substituted 50 for y here. They substituted 130 for x because that's our weight on Earth, and they figured out what the constant rate of variation is, which is 5/13. 50 divided by 130. And then they gave us a direct variation equation. Pretty cool, right? And then they asked us to graph the function by picking some values for x and solving for y. We could do that the fun way, or we can do it the hard way. I'm gonna do it the fun way, which is math way. I just copied the formula that was given to us. Boom. Let's see what happens when we graph. And there it is. There's our graph. I do want to point out that any direct variation equation is going to have 0, 0 as a point. Let's see if they can give us a table of values. I don't want to pay you. Huh. Oh, darn it. Okay, well, you can plug and chug to come up with tables of values. Weight on the moon, y varies directly. So this is the U try. Weight on the moon, y varies directly with weight on Earth, x. A person who weighs 100 pounds on Earth weighs 16.6 pounds on the moon. Find the constant variation k, write the equation that relates weight on Earth and weight on the moon, and graph the equation. All right, so if you want to pause the video at this point and try this on your own, I encourage you to do that. And then when you have an answer, you can just restart the video and see if you're right. Weight on the moon, y, varies directly with weight on Earth, x. So we know that y is equal to kx because it tells us that there's a direct variation. A person who weighs 100 pounds on Earth weighs 16.6 pounds on the moon. Find the constant variation k. So a person who weighs 100 pounds on Earth, that's our x. So k times 100 equals 16.6 pounds on the moon. So if I divide both sides by 100, I can solve for k. A 16.6 divided by 100 is 0.166. You can use a calculator if that sort of digit math is tricky for you. And 100 divided by 100 is 1, so I'm left with k. So k is equal to 1.66. Nope, that's wrong. K is equal to 0.166. Now write your equation for direct variation. Okay, well, that's y is equal to k, which is 0.166 times x. Let's clear the drawing to make it a little bit neater. Okay, create a table of values and graph the equation. Desmos is probably the way to go on that. I'm reluctant to use Desmos. I don't know why. I just have a thing. Let's see if it'll give us graph using a table of values. I found it. Boom. Okay, here's my table of values. I can paste that right in. I think here's my picture. You can take a screenshot of this. Let's see if I can just copy image by right-clicking. I can't, that's why Desmos is better. You can take a screenshot and copy the screenshot in, or you can stop being resistant and use Desmos. And by you, I mean me. Okay. For the data in the table, does y vary directly with x? If so, write an equation for the direct variation function. So what do you need to multiply 4 by to get to 6? 3/2. So I'm going to use this on a calculator. What do I need to multiply 4 by to get 6? I'm going to say 6 divided by 4. Let's convert to a decimal. 1.5. Okay, I like that. What do you need to multiply 8 by to get to 12? Or is 8 times 1.5 also 12? Let's say that. It is. Okay, that's a good sign. And what's 1.5 10 times 1.5? 15. Wow, okay. So what does that mean? Well, that means that k is 1.5, right? It was consistent through all of them. So this is a direct variation function, at least for the numbers that they've listed. Okay, B. They are going to walk us through it, so I'm not going to do this to quite the same detail. To get from -2 to 3.2, -1.6. To get to 1 to 2.4, 2.4. We're done. 1.6 is not the same as 2.4. This is not a direct variation. I can't write this expression in the form y is equal to kx. Like I can this one here. Okay. For the data in the, oh, this is it. We're almost there. For the data in the table below, does y vary directly with x? If so, write an equation for the direct variation function. Okay, I'm going to do this in a little bit more detail so that you can see what's going on here. So if this is a direct variation function, that means that y is going to equal some constant k times x, which means that y 2.25 needs to equal -3. I'm just going to switch my k and my x so that it makes a little bit more sense, times k. -0.75 needs to equal 1x. So I'm just going to write an x. -3 needs to equal 4x. Okay, well, I'm going to look at this one. Look, I'm sorry, I made a mistake. My bad, guys. That was really confusing. That was meant to be a k. Okay, well, funny enough, because x is 1, so this is 1k, right? And this is also meant to be a k. Gosh, I really went off the rails. My bad. What I kind of dig about this question is that I know what k is, because in the case of x is equal to 1, I don't have to do any math at all. This math here, I can divide both sides by 4, divide by both sides by 4, and I end up with -3/4. That's -3/4, which is -0.75. Okay, so that these guys match. So far, so good. Here, I know that k is going to equal 2.25 divided by -3. And if that equals -0.75, I'm good. So I'm just going to, I know it's going to be negative because, and a positive divided by a negative is going to be a negative. So let's see what we got here. 7, 3 can't go into 2, 3 can go into 22 7 times. 7 times 3 is 21. 1, 5. 3 goes into 15 5 times. Again, I know it's negative because the 3 is negative. So yes, this is equal to -0.75. So look, I'm super constant. All right. No pun intended. So my answer here is yes. Write an equation. Y is equal to, I can go down here. Y is equal to -0.75x. Okay. Direct variation. Y is equal to kx. FYI, k is the slope. All right. Let's look at the quiz. So you guys know the drill. If I mean to do that, if you are if you haven't done the quiz yet, please do it and come back to me. Okay, you back? I'm back. Here we go. Zoom. What are the x and y intercepts of the equation? It's the wrong quiz. Come on, teach. Sorry, please hold. Module 5, lesson 2, we're doing direct variation. Let's see if this makes more sense. Suppose y varies, sure does. Suppose y varies directly. Guy here. Suppose y varies directly with x and y is equal to 72 when x is 6. What direct variation equation relates x and y? What is the value of y when x is 10? Okay, 2 parts of the question. What direct variation equation relates x and y? What is the value of y when x is equal to 10? All right, so y varies directly with x. So we know that y is equal to some number that's constant, k, times X. That's a given. They tell us that. And I also know that when Y is 72, that some number times 6 is equal to 72. So all I need to do now is solve for that some number. I'm going to do that by using the inverse operation to multiplication and divide by 6. That goes to 1. 72 divided by 6 is 12. And that is equal to K. This is not the answer to the problem. It's not what the problem is asking for. The problem is asking for what direct variation equation relates X and Y. So here's the answer. Y is equal to, because this is what a direct variation equation is meant to look like. This is the form of it. K is 12. X. Bum, bum, bum. Okay, so the next part of the question is, what is the value of Y when X is 10? Well, now that I have an equation, I need to substitute 10 in for X and evaluate. Okay, Y is equal to 12 times 10, which is 120. You can use a calculator if you need it. Y is equal to 120. So what's in red there are your answers. Okay, question number 2. Suppose the cost of renting a scooter varies directly with the number of hours. It costs $37.50 to rent a scooter for 5 hours. What is an equation that relates the number of hours X to the rental cost of Y? All right, well, we know that these two things are going to vary directly. So it's going to fit the form of a direct variation equation, or Y is equal to KX. And then we know that hours are X, and we have a number here for 5. So X is equal to 5. And the rental cost total is Y, that's $37.50 when X is 5. So I can substitute these back into the equation. I'm going to say 5K. You can just as equally say K5. I'm going to solve for my K. 37.50 divided by 5 is 7.15, I want to say. Let me do it the long way. I could always pull up a calculator, but why use a calculator when you know long division? Oh, but I was wrong. I'm glad I checked. 750. Okay, so K is equal to 750 equals K. Okay, so what is an equation that relates the number of hours X to the cost Y? I'm going to use my direct variation equation because it tells us that the scooter varies directly with the number of hours, the cost. And I know what my K is now. So Y is equal to 7.5 X. Graph your answer from part A. Okay. let me just scoot this down a little bit. So I'm going to clear this up. You can always scroll back if you need the answer. I know that y is equal to 7.5x. I also know that this is linear because my slope, my direct variation is constant. I know that 0, 0 is a point. I don't want to use 1 because then I get into partials because I'm not dealing with a whole number. But if I multiply 7.5 by 2, if x is 2, y is 15. So that's a pretty easy point to use, right? So let's see what we got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 15, 2. Boom, boom. Wow. Okay, that's an awful line, but you can always type something into Desmos. Oh my gosh. Okay, be better than me. Be better. Just be better. Type this into Desmos, tell it to graph, and then just paste the graph. Or you can just, if you're doing this by hand, it's way easier than me doing it on the mouse. Sorry. Okay. Let me look at number 3. For the data in the table below, does y vary directly with x? If it does, write an equation for the direct variation. Okay, so y is equal to kx, right? This is what it means for two variables to be directly, to vary directly with each other. So when y is 6, x is 3. So 6 is equal to k times 3. 10 is equal to some number k times 5. 14 is equal to some number k times 7. Well, if I divide both sides by 3 here, I get k is equal to 2, because 6 divided by 3 is 2. If I divide both sides by k on the second data point, 10 divided by 5 is 2. And if I divide both sides by 7 on the third data point, 14 divided by 7 is 2. So I have a consistent constant that's the same for k. But the question is not asking us for k. It's saying if it does, which it does. So the first part of the answer is yes. And then if it does, write an equation for the direct variation. That's y is equal to 2x. That is it. Okay. I know that was really fast and furious. This is just meant to give you something to grapple with if you're if the material is not coming super readily. Your teacher, if that's me, or if it's not, doesn't matter, is here for you. So you just go ahead and shoot us an email if you need more help. Okay. That is module 5, lesson 2. And I'm out. The video didn't stop. It's still recording. It's recording Mario. It's me, it's Mario. Okay, bye.